Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thanks for joining us today. I'm your host, Henry Regis, and along with me is my co-host, Nolan Duskin, here at the Colorado Climate Center and at Colorado State University in Fort Collins, Colorado. Behind the scenes today running our program are Zach Schwalbe and Noah Newman. For those of you who are unable to join us for our live broadcast, we'll be recording this broadcast today for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today we will look at the subject of climate monitoring. We will learn about major climate monitoring efforts going on in NOAA and how our CoCoRaHS observations fit in. And we're really excited to have an old friend of ours with us today, Deke Arndt. Deke is the chief of the climate monitoring branch at NOAA's National Climatic Data Center in Asheville, North Carolina. And his branch is responsible for routine and special reporting of the status of the Earth's climate system, all the way from large global phenomena like global temperature, global warming, to regional occurrences like drought and weather extremes. Before coming to NCDC, Deke spent about 15 years at the Oklahoma Climatological Survey in Norman, Oklahoma, and Deke holds degrees from the University of Oklahoma, and I'm assuming, actually I know he's a fan of Sooner football. There's probably some Sooner fans out there on the broadcast today. Deke, welcome. It's great to have you with us today, and we're so glad you can join us for this broadcast.
Thanks a bunch, Henry. Can you hear me, Henry?
You sound very well. Very good. You should be able to pull up your screen now. We'll try it. Now I think you're on. So.
Okay.
I don't see your screen.
I see the screen here. This is Nolan.
You do.
Okay. Great. So I will go ahead and get started. I want to thank you for inviting me today. It's a real thrill. During my time in Oklahoma, I worked in an office that tried to do many of the same things as the Colorado Climate Center, that's basically taking data and information and trying to help make it useful for the people in my state. And we always looked up to the things that the folks in the Colorado Climate Center did. So it's a real privilege to get to join this program. Today we'll just talk about a few things monitoring the climate system and kind of where the data fits, and a little bit about what we do and what we're seeing in the climate system, and then a little bit about the state of the science and how climate and climate change may inform or not inform some of the weather that we're seeing here in the U.S. Let's see here. All right, so like any presentation, the commercial will be short, I promise. So I'm from the National Climatic Data Center, which is in Asheville, North Carolina, in the Appalachian Mountains of North Carolina. And if I'm not mistaken, I think it was a town once tormented by a college kid named Henry Regis. So we're here at a federal facility. What the Climate Data Center is, and I'll say NCDC many times, and what I mean is the National Climatic Data Center, it's a place where a lot of the weather data that you see on the evening news and elsewhere kind of goes into retirement. So in this screen, we're seeing a picture of a guy showing temperatures in Florida. Well, those numbers, that 85 degrees at Jacksonville, will eventually find its way here to the National Climate Data Center, which is essentially the nation's weather data library. And our first mission is to basically store and protect that data to make sure it's available for future generations. And then we also provide that data to scientists who want to study the long-term trends in both weather and climate as well. And we employ some of those scientists that do that as well. There's a great deal of data here, 10,000 terabytes, whatever that means. I don't know what a terabyte is, but I know we store about 12 billion Kindle books worth of information here at the center, and we add about 6 million Kindle books to that total each day. And that's data from around the world. It's not just U.S. data. We're one of 3 world data centers. We cooperate with colleagues in the United Kingdom and in Russia to store all of the world's weather and climate data. One of the things that we do, you may be familiar with, are the normals. So when the weather person says today was 2 or 3 degrees above normal, those normals are established every 10 years based on the most recent 30 years worth of data, and one of our efforts every decade is to update the normals for both temperature and precipitation, and a lot of ag-sensitive normals, growing degree days, and so on. So that's one of the things we do here. And then to get into kind of climate monitoring, when you combine both these long-term products like normals with everyday data, you can begin to put today's weather or yesterday's weather or last week's weather into a historical context. And when you do that, you're starting to talk about applied climatology, which is what many of the CoCoRaHS leadership, that's the community that they come from. So what we're looking at here is just an example. The gray sleeve, the gray envelope that stretches across the screen from left to right represents the average high on the top and the average low on the bottom for Roanoke, Virginia in the months of March, April, and May. And then the blue bars represent both the high temperature up top and the low temperature down at the bottom for every day that was observed in 2013. And there's nothing really special about the climate signal in this. It just shows a few things. One, the normal high and low is very smooth and kind of gradually increases as you go from March to April to May. As you would expect, the days get warmer and the nights get warmer as you get later into the spring. But the weather that we actually observed in Roanoke, at least from highs and lows, was kind of all over the place. Bounced around. It spent a few days at a time either warmer or cooler or kind of within the normal period, and this is what we see and call weather. So this noisy pattern that we see where we saw a few days of warming up and a few days of cooling down, all of that averages together to come up with these statistical values when you hear, for example, what we just reported today, that Eastern Virginia was very near normal for their springtime temperatures. And this is what normal looks like on a day-to-day basis. It's bouncing around these normals, but the long-term average roughly worked out. So when you start talking about long-term climate and averages and expectations and normals, and you start to compare those with day-to-day observations and what we're seeing now at the moment or during this season, that's kind of a special place in the climate services community that is called climate monitoring. And there are people that do this around the country, people that do this for their businesses or for their states. My branch happens to do it for the country, but what we do, what the folks on the screen are charged to do, is basically monitor and assess and describe the state of the climate and how what we see fits into what we would expect in the long run. So most of what I'll show and talk about today kind of fits somewhere close to this mission that our branch has to kind of better understand and give an accurate play-by-play and color commentary of what's going on with the climate system for people in the U.S. who are interested in that. These are some wonderful people to work with, and I've been really privileged to share the last 4 years with all of these folks. So just a little bit about me, where I'm coming from. I'm a meteorologist. I basically studied jet streams and severe weather and patterns in weather, and I got into drought in the early 90s for a really good reason. I needed a job, so I took all of that weather background and tried to apply that to drought, and kind of got hooked on this long-term kind of statistical and climate scale approach. Then I got into climate services, helping people find data and understand data, and then I got into the big picture of climate, and that's what brought me here to Asheville. So just to emphasize, and this will become really, really apparent in the next 30 minutes or so, my meteorology background is just a tiny sliver of this big climate system that we're trying to better understand day by day and month by month. Before we begin, and I assume this presentation will be available online, so I'll dwell on this slide for a minute, but a lot of the information that we're about to churn through, and there's some more resources at the end, come from these four sources. There's a State of the Climate report that is put out every year by our Professional Meteorological Society. That's essentially the annual checkup, the annual physical of the climate system. What do we see? What were the vital statistics, and so on. The National Climate Assessment is, the word assessment when we talk about climate is what are we seeing, how well are we seeing it, and how does it fit into what science says our expectations are in climate. So every 4 years, the nation, many agencies and academics get together to produce a multi-chapter assessment of what's happening with our climate system and what it means, and is it expected or unexpected, and so on. We'll talk a little bit. Yeah.
Just to let you know, we'll put a link to these on the CoCoRaHS WeatherTalk webpage under your section. So we'll put those on there, and folks can access them from there.
Super. Thanks a lot, Henry.
Sure.
All right. We'll talk a little bit about extreme weather. What is up with some of the weather patterns that we're seeing, and how do they or don't they relate to climate? And some of the data that we see comes straight from our shop here. So. Just the annual State of the Climate, the reason I put this on here today, we actually just today sent the 2012 State of the Climate report to the printer. So the meteorology community will be seeing this volume in about a month. And we're privileged to have about 400 authors and editors from more than 50 countries around the world contribute to this. And this is one of the major kind of long-term activities we do here in the branch, is to try to coordinate all of this input from glacier specialists and oceanographers and biologists and all of these specialties that we have no expertise in, try to cram it into about 200 pages so that people can read. So, and then finally, we'll talk a lot about the monthly kind of state of the climate, and I won't dwell on this too much, but this is a monthly update. The URL here is at the bottom, and it's basically a system of reports that we write that that describe, both with a written report and with lots of supporting data, what is happening on these different scales, whether it's globally or within the U.S., or whether you're concerned specifically about drought, or you just want the big picture climate, and so on. So we'll refer to these a little bit as well. So I apologize for the commercial, but that's where all of that comes from, and that's the perspective that I'm coming from today. So before we talk about weather and climate data and whether and how this data that we're looking at and that CoCoRaHS observers are taking, before we talk about whether that matters, one question is, well, does weather and climate matter itself? And we're going to go back in time a little bit and see what some historical perspectives are on the weather and climate. So we're going to look at several important kind of events or writings in human history. So, so here's a passage from a guy named Calonne in 1959, and it talks about how on a summer day he left for Jamaica, and he noted that the climate hadn't changed and that there was rain, and this guy who happened to be a sea captain wrote that the forests were contributing to this rain, and back where he was familiar with in the Canary Islands, since they removed these forests, the weather and climate had really changed. And so although that is credited to 1959, Calonne is actually Christopher Columbus, and he wrote that in 1494. So as a kind of a famous mariner, he was really into the weather and climate. And even as early as the 15th century, people were trying to make connections with things that they saw on the ground and things that they saw in the sky and how these things affect each other. So at least according to Christopher Columbus, he was very interested in learning how this climate system, this weather system, worked. Going back a little farther to the Mediterranean, this is 1,000 years before Christ, and this is a description from the Iliad, and it's actually from the Odyssey, so the old Greek text that tried to describe the world as they understood it. And he's basically describing the Greek version of heaven here, and he says, you know what, in heaven the wind always blows from the west. And that was, what, 3,000 years ago. They were already making observations like, you know, when we get this west wind, the day is really nice, at least here where we live. And one of the things, if you go back and you read these epic poems, they spend a whole heck of a lot of time describing the weather and climate of a place. And it is obviously really important to the culture at the time to just know what happens and when it happens and where it happens and what to expect when you visit a certain place. All right, so also hitting some really important documents from the past, and we'll hit the New Testament and the Old Testament as well. Again, kind of littered with, when we see winds from a certain direction or weather conditions of a certain type, we tend to expect different outcomes. So we've been writing and recording and passing along knowledge about what we know about weather and climate for thousands of years. And the one thing that we have developed in the last little more than a century is a systematic way of putting numbers on all of this. And you guys on the call are a huge part of that. So from a precipitation perspective, you're helping put numbers on to this eternal human quest to figure out what do we know about this climate and weather system, and how can we quantify what it does to us. So you are not just part of a program that has really, really blossomed in the last decade or so. You're part of centuries of drive to understand and describe and pin numbers on a climate system that's always been important to us. So you are definitely part of a big, big, big picture process. All right, so that's enough of the philosophical stuff. So what is the big picture? What's going on with the climate system? So one of the things we do here, and many other people do in academics and data centers around the world, is to try to estimate the globally average temperature. So when we hear about global warming and climate change, one of the metrics that we use quite a bit is the globally average temperature. And that's what's represented on this graph. If you look from left to right on all of the time series that we may come across today, left is the past and right is the present. So this happens to go from 1880 on the left to 2012 on the right. And these blue crosshairs show the average global temperature compared to the 20th century average. So years that were warmer than the 20th century average are above that dark line, and years that were below or cooler than the 20th century average are below. And you can see some trends. You know, there's a clear trend that the recent years are warmer than the more distant years in the past. And you can also see that there is a lot of up and down. It's not just a steady climb. There are a lot of year-to-year noise, and there's even times where we spend a few decades not warming, but the overall trend is up. And if you want to remove some of that noise, you use methods like, well, let's just take the average of each decade. So what each one of these red bars represents is the average of the 10 years that went into that decade. And then you get a more clear picture that we warmed in the early part of the 20th century, and then we really warmed in the last part of the 20th century. And we had the two warmest years on record were in 2005 and 2010. So what we see is, again, not every year is necessarily warmer than the last year. But if you're in a particular neighborhood, if you're in the 2000s, you know about where you're going to be. The warming is over the long term. pretty unmistakable since the mid-1970s. But that being said, no one was ever found dead under a trace of global temperature. So, this is one way to measure the temperature of the planet, but it doesn't really mean a lot in our day-to-day lives. The reason it means a lot is because this may affect some of the things that we experience, and we call those things weather, and sometimes we call those things seasons. So just a few ways to look at that. That 2012 value at the very right, if you look at that on a map, you can see this is what 2012 looked like. And even during 2012, which is one of the warmer years on the record, but not the warmest, you can see that around the world, parts of the globe were warmer than average, and parts of the globe were actually cooler than average. And so that 2012 value represents an average of a lot of different local conditions. We happen to have a really, really warm year in 2012 in North America, and that contributed to pushing 2012 up towards the top of the list. But folks in Alaska and folks in Asia and even parts of Australia actually had a fairly cool year. So one of the things, if you look at the last graph and the noise up and down, and then you look at this map, one thing is clear is that the global temperature is really just an average of a lot of different local conditions. But when you pull back and you say, okay, well, let's look at the trends. Let's look at the long-term signal, not just 1 year. So here is, since 1880, every box on this map that has a color has had consistent data since 1880. And you can see, okay, when we look at the last 130-something years, we do see some trends. We see that almost everywhere on the globe is getting warmer, or is warmer now than it was. And we see that land areas, by and large, are warming a little more quickly than ocean areas, which makes sense, and we'll talk about that down the road. And we're seeing a little bit that the high latitudes, the more northern land areas, northern Asia, Russia, Canada, Alaska, are warming a little more quickly than the rest of the globe as well. And the next slide we're going to show is not just the trend since 1880, but we're just going to look at the trend since 1970, and these are on the same scale. So I'm going to toggle back and forth just a tad, and we can see that since 1970, the warming is accelerating, and it tends to be focused on land areas, and it tends to be more dramatic anyway, or the rate of warming is faster, again, in these what we call high latitude, these more northern or more poleward areas of the northern hemisphere. So that's part of what we do here in monitoring, is to try to figure out, okay, which data sets are the best that we can use, what do we need to do to correct some of the issues in the data set so that we can get the truest signal that we can, and then how can we turn around and do an analysis and share this with people who may be interested in seeing stuff like this. So again, that's just temperature, and temperature is only a piece of the climate system. It's just one way of measuring the climate system. And to really understand how the climate is changing, you can't just solely focus on temperature. Temperature itself is important, but what you guys do is you measure precipitation, and the way that water falls or doesn't fall is so important to life that precipitation is one of the most important things that we can track in the climate system. And we want to know a little bit more about the upper atmosphere. So how are conditions in the atmosphere way above our heads changing, and how might that affect weather patterns that we see, and so on. So monitoring the climate, although the global temperature is pretty iconic and people kind of quickly understand or at least relate to a global temperature, our job is to try to do the best that we can to comprehensively monitor the climate. It's like going to the doctor for your annual checkup. If the doctor only took your temperature, you wouldn't know much about what you're going through. The doctor has to do a battery of tests. Maybe they take your blood pressure. Maybe you hop on the scale. Maybe they take a blood sample. And using those batteries of tests together helps to pull together a better picture of what's going on with your whole body. And so that's the same type of approach that the people who observe and monitor the climate are trying to do. All right, so where do those temperature numbers come from? This is a map with colored dots on it that shows where stations are that we use to help monitor the land part of the global temperature and how long they've been in operation. And you can see some distinct patterns. You can see the U.S. is probably the best instrument. The U.S. and Japan probably have the most dense instrumentation for, and this is for temperature, of anywhere in the world. Europe and Turkey and parts of Australia have been well monitored for quite a time too. But you can see there are some holes. And part of monitoring is to try to determine whether we can fill in the gaps in those data sparse regions, or whether we just need to give up and say we can't make a number for that. And that's part of the decision process in climate monitoring as well. All right, so global temperature, again, is not the only metric of a changing world, and global temperature, for better or for worse, has become quite controversial in the blog world anyway. And so one way that we try to determine the validity of those global temperatures is to look at different components of those temperatures and different data sets that are put together to try to validate what we're measuring with the global temperature. So one way that we've separated it out is let's just look at those land stations and what do they see. And these 4 lines on this graph stretch from 1850 on the right to 2009, actually on the left, on the 1850 on the left and 2009 on the right. And these are 4 different data sets, 4 different combinations of those stations and what they are measuring for the global temperature, at least for the land areas of the planet. And you can see a few things. They don't all begin on the same date, so they're made up of slightly different station combinations. You can see that they're not always in complete agreement on individual years, but you can also see that the long-term trends that they're seeing, these decade-to-decade patterns and especially these longer-term patterns, are in complete agreement. So they're not always hitting the same notes, but these different data sets are singing the same songs. And this is one way throughout all of our data sets that we try to build and understand and build confidence in what we're observing. And one thing you'll notice, again, the long-term signal is a lot like the stock market, which many of us are familiar with. So you can see on this graph happens to be the Dow Jones Industrial Average over the course of the last few decades. And you can see from day to day and week to week and month to month, there is a lot of noise up and down, but there are some distinct multi-year events that drive it, that push it up locally, that cause a brief warming or cooling or up or down trend in the local neighborhood. And then there's a distinct long-term signal. So there's, in many ways, the different pieces, the different variables of the climate system, temperature in particular, is going to see some ups and downs, some leveling out, some peaks and valleys, but the long-term signal is up. And again, it's not just temperature over land. We see the same kind of consensus data set evaluation in the temperature over the oceans as well. Again, multiple indicators singing different notes at different points along the way, but overall the song that they're singing is the same. The amount of, represents different ways of measuring the amount of heat that's stored in the upper 700 meters of the ocean. So the top slab of the ocean, this represents essentially the number of calories, if you will, the amount of energy that is being added and stored into that layer as well. The agreement on individual notes is not there. So there's quite a bit of disagreement on individual notes. But again, the long-term signal from these different data sets it's pretty coherent. And then we look at things like, here's sea ice. So this is the footprint of sea ice that we see every September in the Arctic Ocean. And these are 3 different ways of measuring the amount of sea ice that we see. So every September, the Arctic ice cap melts back to its annual minimum and then grows outward from there, kind of expands through March, and then melts back to every September. So this is the September value, that minimum footprint. Where does it retreat to in its smallest month? And you see the sea ice is getting smaller and smaller. And for a time, 2007 saw the smallest retreat of sea ice, and then since then, 2012 is now the smallest footprint of sea ice. So it's not just temperature that's an important indicator in our climate system. It's other measures as well, and these are the types of things that we track. So all of these together are saying, yes, the world is warming, but they don't say why. All of these indicators together are saying, you know what, we all agree, it's getting warmer down here, all of our frozen stuff is going away, the temperatures are getting warmer, the humidity is going up. I didn't show that, but this humidity down here where we live is going up. And they all unanimously indicate, yeah, it's getting warmer, but it doesn't say why. And this next indicator does say why. So this is the temperature in the stratosphere, which is tens of thousands of feet above us in the atmosphere. And it shows that while everything down near the surface where we live is getting warmer, the upper atmosphere is actually getting cooler. And if there was something going on with the sun or our orbit that were to be warming the world, the outer atmosphere, the upper atmosphere, would also be getting warmer. But the fact that we're getting warmer down here and we're losing ice and we're losing glaciers and we're increasing humidity and it's getting warmer over land, it's getting warmer over the ocean, while the upper atmosphere is cooling off, is kind of the smoking gun that the warming that we're seeing down here is based on changes in the composition of the atmosphere. So this is the evidence that we see that the greenhouse gases that are trapping heat low in the atmosphere are doing so at the expense of temperatures in the upper atmosphere. And again, multiple data sets that disagree on different notes along the song, but they're singing the same song. And the spikes in this, that there are 3 spikes, one in the 60s, one in the early 80s, and one in the early 90s, and those are 3 tropical volcanoes that actually shot a lot of material up into the stratosphere and temporarily made it warmer. So these are the types of issues we deal with in data. So that's the last of the really, really nerdy global scale kind of big picture global warming stuff. And we see these different indicators that all agree that things are getting warmer. But again, what does that really mean? Why does that matter? Does that matter? And the answer to that question is also begs another question, what's the relationship between weather and climate? And we'll spend basically the rest of our time today just talking a little bit about what we've seen and how that relates to climate. So this is what I call our class picture of the CONUS, or the contiguous lower 48 United States. We've lined each year up, we've been observing a CONUS temperature, so this is the average temperature of the 48 states, since 1895. And if you line them up, these are the 5 coldest years for that area, down in the lower 50s. And these were the 5 warmest years that we'd seen. And then there were 107 other years kind of in between. So this, again, is what it looks like if you lined up the years, kind of ranked them from coldest to warmest. And then what we saw last year was amazing. So we saw a temperature that was a full degree Fahrenheit warmer than anything we'd seen since at least 1895 here in the contiguous U.S. And most of you live in areas that were record warm or very nearly so for the duration of 2012. And people see or experience something like this, and they ask, well, is this just natural? Is this just a random, really big event, or is this a changing climate? And the answer for me is yes, a little bit of both. So this was a huge, big event over much of North America. but it comes in the context of gradual warming. So some of the other things we've seen, and this is just a list of the states that have had their warmest or coldest or wettest or driest something in the last 3 years. So from 2010 through 2012, the states that you see in red, so there's a big cluster of red states in March of 2012, those were states that had their warmest March on record. You can see in spring of 2011, and many of you were observing record spring rainfalls in much of the Midwest and Ohio Valley and Northeast. And so we've seen in the last few years a great deal of extreme behavior, at least from a month-to-month and season-to-season standpoint. We've seen a lot of really warm events. We've seen some cold events. We've seen a lot of really wet and really dry events. And it's a natural question to ask, what's the relationship between what we've seen over the last 3 years and the long-term climate? And it's not just temperature and it's not just rainfall. We've seen some pretty big snowstorms in the last few years as well. And so the relationship between weather and climate boils down to one piece of literature, I think, that does a great job of describing this relationship. And it was written in the 70s by a guy named Stallone. And this is pretty much what it is. So you can see Rocky the boxer on the left, and he's weather, and you see Mickey the trainer on the right, and he's climate. And they have a relationship. Mickey isn't out there throwing the punches. The trainer trains the boxer throws the punches. And that's the relationship between weather and climate. If you change the trainer, you will change over time the punches that the boxer throws. He'll throw certain punches more often or less often or more effectively or less effectively over time based on this long-term influence of a mentor or a trainer. And that is, in many ways, the relationship between weather and climate. If I change the trainer to a different trainer, I'm still not going to be able to tell you what punch Rocky's going to throw with 2.5 minutes left in the 8th round of his next fight. But I can tell you, based on the new trainer, he's going to throw a lot more left hooks. And that's kind of the assessment. That's kind of the way we have to approach the relationship between weather and climate. Because we're not yet at a place where we can examine an individual event and say, oh yeah, that was climate. Or that was 47% climate and 53% weather. But what we can do is look at weather events over time and see how they are changing and how the ingredients that come together to produce them are changing. And so here's an example. This is another graph from 1910 on the left to 2012 on the right. And these bars on the graph represent each summer during those 103 years. And the bars represent the area of the country that was either in extremely warm conditions for summer in red or extremely cool conditions for summer in blue. And you can see a pattern that recent years we've had a lot more big heat in our overnight summer temperatures in the U.S. But you can also say, each one of those years, each one of those spikes, each one of those summers had weather patterns that helped dictate some of those events. We may have seen a jet stream pattern or a blocking pattern or a persistent ridge or a pervasive and persistent body of warm air, and those have a lot to do with weather, and that would be exactly right. But you could also take a look at this long-term picture and you say, you know what? Over time, we're seeing these patterns, these ingredients, these weather conditions come together more often, and that is the influence of climate. They have this relationship where the boxer is still going to do things from second to second and minute to minute and day to day that are determined by the boxer, but this influence of the long-term climate it begins to show up. And one of the things that's really important on overnight temperatures is when it's warmer late at night, people run their air conditioners longer. It's difficult for livestock to gain weight. Public health suffers a little bit. If people are poor and don't have air conditioning, they're warm longer into the day. So this is expensive. It's not just a measure of climate change. There are real impacts tied to this increase in the footprint of big heat that we're seeing in the nighttime, in the summer nighttime. But we also still have things like El Nino and La Nina, and we won't go into the dynamics of all this because I would end up in the fetal position here in my office. But El Nino and La Nina also influence seasonal outcomes as well, and that's a very natural phenomenon. El Nino and La Nina, in the late 20th century, we learned quite a bit about it, and we learned that El Nino and La Nina, depending on what phase we're in, can influence the outcome of seasons that we see here in the U.S. One of the things that we saw in the La Nina year of 2011 was very wet conditions in the Ohio Valley in the Northeast and very dry conditions in much of the South, and those are typical of what we often see when we have a La Nina. So these are still natural factors on top of a changing climate that can influence outcomes on a season-to-season, month-to-month kind of level. So my last kind of relationship, what is the relationship? I have a 10-year-old son, and I'm sure many of you have a lot of experience with 10-year-old boys, but if I were to describe my son, I would call him a kind of impulsive. He's got a pretty short attention span. He's really sensitive to the world immediately around him. So he is really responsive to local factors. If he's got noisy kids around him, he's real sensitive to that. He is prone to occasional extreme behavior if the right set of ingredients come together. And I may mean extreme good or extreme bad, whatever. He can really get off the charts if the right things come together to influence his day. The great thing about him is he forgets these things quickly and he moves on. And if my kid didn't already have a name, I would name him Weather, because that describes pretty much exactly how weather kind of relates to the bigger picture climate. And my kid can be impulsive and extreme even in a very stable environment. So even with an unchanging big picture influence, that kid is prone to bouncing around and causing extreme behavior or extreme weather, if you want, even with an unchanging environment or an unchanging climate in his house. But if you were to change the climate that same kid were growing up in, and you would replace the stable climate with one that is a little less stable and a little more prone to change over time, you'd notice some things. And that kid would still be impulsive. That kid would still be responsive and sensitive to his immediate environment. He would still spend months at a time hanging out with influential friends that shape his week-to-week and month-to-month decisions, regardless of the parenting that was going on. But he would be getting into different situations more often if you change that parental influence. And this is an important point. The drivers of his days would be really similar. The things that shaped his days would be really similar. He would be sensitive to the same ingredients coming together, but the trajectory of his life would have changed. And this, again, is a description, this parent-child, mentor, apprentice, coach, athlete kind of relationship. We often get asked, well, was such and such weather or was it climate? And it's both, and they have a relationship. And that is the relationship that we have. So to try to put some numbers on that, we track things. So for example, with tornadoes, again, an extreme weather event, if you were to just look at the graph of the number of tornadoes that we've observed in the U.S. over time, you'd see that it's unquestionably going up. And at first glance, you would think, oh, yeah, well, we're getting a lot more tornadoes. There must be something driving that. And there is something driving that, and it's that we're a lot better at detecting them now. We're actually not seeing a big change in the number of big tornadoes that we see, but we're a whole heck of a lot better than we were in the middle 20th century at understanding when they might form, using tools to detect them, and going out and verifying that they happen. So one of the challenges in climate science is to try to not get taken in by trends in the data that may have non-climate factors that are driving the trends. And tornadoes are certainly an example of that. If we were to look at this graph at first glance, we would think, oh my gosh, the number of tornadoes has gone up 4 or 5 times what it used to be, and when in fact we're just detecting 4 or 5 times more than we used to. So one of the challenges in climate science is to examine the physical relationships and the understanding and the way we're able to observe all of these things, and this is where it ties back again to CoCoRaHS, a dense network of daily observations measured in the same way from time to time, over time, and available in real time, is a big help, not just to the weather and flood and forecast community, but to the long-term study of precipitation patterns as well. The numbers that you're typing in to your account, they go actually here to NCDC, and we put them in our precipitation data sets, and we use them along with other precipitation data to try to get the cleanest record that we can. So what can we say about extreme events? If counting things is a little problematic, like this number of tornadoes, a lot of extreme events are born from a set of ingredients. And what we can do for tornadoes, the example would be warm, moist air at the surface, something we call atmospheric instability, and something we call wind shear, are kind of ingredients that come together to produce the potential of tornadoes. And while we may be counting more tornadoes as a testament to the weather community, to be honest, the way we track instability and wind shear and moisture at the surface hasn't really changed a lot. So a lot of climate scientists keep track of the ingredients that go into these different extremes rather than counting the extremes themselves. So what can we say confidently about big weather versus climate? So what we can say confidently is big heat is increasing and is expected to continue. So we're seeing more episodes of unprecedented or near record heat throughout the U.S. and also the globe, but the U.S. is where we have the best data. And that means that heat events are either bigger, they cover more ground, they're longer lasting, they last many more days, or they peak at a higher level than they used to. Again, on average, this is all on average over time, and that's probably the most confident thing we can say. We are seeing more big heat, and we expect that to continue. The next most confident thing we can say is we are seeing more big rain, and this is where, again, where you come in. We are seeing more events, and we are seeing more and more of a season's or a year's worth budget of rainfall coming in single events. So I'm from Oklahoma, and we have central Oklahoma roughly 35 inches a year on an average year, on the so-called average year. And what we're seeing, for example, in the plains, and especially in the Midwest, and especially in the Northeast, is that 35-inch average over time, and whatever value it is for whatever part of the country, is coming in fewer doses, and the doses are bigger. And that's consistent with what we would expect in a warming world, because a warmer atmosphere can carry more water to a storm system and then deliver more water on the ground. And your observations are going to play a huge role in really helping us refine this understanding, because rain doesn't, temperature happens like a blanket, over space. There aren't a whole lot of really local long-term temperature signals, but rain falls in bizarre patterns. Rain is very local. Heavy summertime rain, the types of events that are getting bigger and more dramatic, that's very local. And the more dots that we can put on the map, the better we're going to be able to understand and quantify all of this. And CoCoRaHS is a huge part of putting more dots on the map with good data. The next thing that we can say is big drought is increasing on a region-by-region basis. This, again, is expected to continue. And the rationale, if you ask, well, how can big rain increase and how can big drought increase? The rationale is kind of twofold. One, if you're concentrating more of your year's rainfall into single events, you're having longer periods of time with less rain in between. And at the same time, if the atmosphere is warmer, it's going to be asking for more water from the soils in the form of evaporation and transpiration from plants as well. So big rain is definitely going up. Big drought is going up less dramatically. And the confidence, the top two are the ones that we're most confident about. As far as violent local weather, which is severe thunderstorms, tornadoes, hail, big wind, and thunderstorms, there's basically no detectable signal currently. It's an active area of research, and they're really looking into how are the ingredients coming into play. For tropical cyclones, which means hurricanes and tropical storms, we expect to continue to see a trend that the average storm is going to be a little stronger over time. The actual number of tropical cyclones that form in a given year is inconclusive. That's still an area of active research. For snow and ice, we would expect that snow and ice would kind of migrate northward compared to where it is now. The data are in a condition that we really can't say a whole heck of a lot. We would expect regional shifts over time. We would expect snow and ice to kind of retreat northward in a typical winter over time. But again, the data's not in great shape, and there hasn't been a coordinated effort to really clean it up yet. So just finally, just the last couple minutes, where do we go to get this kind of information? Here are some URLs, and Henry and Nolan said that they would provide some of these. So NCDC, our kind of institutional home, is up on the left. NOAA, our parent agency, operates a climate.gov. We actually run that here out of NCDC. You can see some more thematic information on climate.gov. Drought.gov actually runs right here out of my branch. So drought.gov, if you need information about ongoing drought conditions or mitigation efforts or remediation efforts or just general communication about drought, drought.gov is an excellent source as well. And finally, the last two links here are for data. That CDO web URL on the left is kind of a map-based interface to go get data. And then on the right, climate information is access to some of the climate monitoring things that we do here at NCDC. And you can see basically this is what did April look like. It was the 23rd coolest on a national scale. And if you cut up the nation into regions, you can see that it wasn't the same across America. If you cut up America into states, you would notice features like that April where the U.S. had its 23rd coolest April. North Dakota had its coldest April on record, and the coldness was really focused in the plains. California and Florida were a little warm. And if you further cut it up, you can get information like that as well. And in that climate information URL, you can actually go get a map, you can zoom in, you can find a station, and actually grab data and play with it yourself if that's what you like to do. And with that, I think that is the end of our planned program today.
Deke, Nolan here. Incredible, and thank you so very much. Thinking of when I was a kid, interested in climatology, and nice background music, by the way.
That was rocky, man. That's
I
cool.
thought you'd like that, Deke. We put that in for your climate
Cool.
versus weather.
But it would have been impossible to envision pulling all these data together over the whole globe so quickly. You're not quite as old as I am, but did you even envision this as you were getting involved in this field?
No, not at all, Nolan. That's a great point. I mean, I think even 10 or 15 years ago, the explosion of not just the infrastructure and the internet and the communications, but the sophistication, the way people are so much more comfortable kind of demanding information. You know, we still have an entire basement filled with paper records here at NCDC, and you know, we systematically try to liberate some of that data and make it electronic. But Nolan, I had no idea that the quickness that we get data from around the world, and it's now available. And that's, I think, ultimately a good thing. It is definitely a management challenge. So.
Well, Deke, thank you so much for this presentation. Very interesting, very informative, answers a lot of questions out there. And speaking of questions, let's go ahead and if you have a question for Deke, go ahead and type it in. We're going to take the next 20 minutes and try to answer as many as possible. We've got one that's a couple on our screen already. Richard in Tennessee says he lives in a very small town in Tennessee. Where could he obtain a daily average chart that would show temps, precipitation, etc. for his local region?
Yeah, so in the climate.gov, www.climate.gov, there is a little widget where you can enter your zip code, and you can get both the average conditions from the nearest site that has a normal and the observed conditions from the nearest site, both of those. So climate.gov is probably the easiest. If you're just looking for temperature and precipitation, you can do that as well, and that's true for many places around the country. And as a plug for the community that Nolan and Henry belong to, and I used to, the vast majority of states also have a state climate office that have even more additional resources beyond kind of what a federal agency can provide, and they may be able to point you to some specialized information that can get in your hands as well.
Thanks, Deke. Here's one from Jan in Southeast Florida, and he's writing, asking that folks are saying that the odds have increased that Florida will be struck by a hurricane this year because it hasn't had one directly hit it since Hurricane Wilma. Can you confirm that past history does not affect the odds one way or the other that will have a greater or less chance of being struck in a year? That was his question.
Sure. So that's true of a lot of high-end events that, you know, the long-term, the long-term history, you know, Florida is very prone to tropical cyclone strikes, and we've basically been able to confirm that by looking at the past history. But it is, he is correct that looking at the last few years, that really doesn't have a whole lot of relevance on what can occur this year. And I'm not in the prediction business, but I do know that the Climate Prediction Center did forecast an active tropical cyclone season for the Atlantic Basin, which includes Florida, this year as well.
Thanks, Deke. Abby writes and wants to know, is the information from the last 200 years enough to predict future weather? So is it too short a period, or is it enough, or what's your opinion on that?
So future weather, if you're talking about what I would call weather, which is what are the conditions going to be tomorrow, you need basically an understanding of meteorology and great observations at the time you make the forecast. So if that's, you know, meteorological forecast isn't really, especially anymore now that there is more data available, there is more computing horsepower available, and the science of meteorology has advanced so much. The long-term climate record is only kind of a background variable for these local weather forecasts. Now, if you're saying, will the trends that we've seen over the last 200 years continue to advance on the big scale, that again is the projections that we make on a climate sense. You know, that we expect to warm by so many degrees over the next few decades. Those again are based on physics and not necessarily based on just extending the trends that we've observed. If anything, the trends that we've observed over the last few decades have helped reinforce what we understand about the physics and have helped make the projections for the next few decades more confident.
Okay, Jerry writes in, and I guess it's kind of a question, a statement. He says, hotter summers are do they create a feedback loop? More air conditioning requires more electricity, which puts more carbon and stuff into the air, ultimately warming the atmosphere further, and is feedback. What do you think of that?
Yeah, so I mean, as an old meteorologist who kind of accidentally got into climate, the connectedness of all of the pieces of the climate system continues to amaze me. So these feedback areas, and they happen both within the natural physical climate system, and then they also happen in the ways that we interact with the climate system as well. And that's what Jerry is touching on, is essentially, yes, if we increase the amount of greenhouse gases in the atmosphere and the major greenhouse gas, carbon dioxide, we will accelerate the rate of the global scale warming that we've already observed. Again, just like the boxer analogy, where we don't know what punch the boxer is going to throw at a specific time in the 7th round, that's the same thing. So if we continue to accelerate the big picture, large-scale, global-scale warming, that doesn't necessarily mean that a particular summer in a particular place in the future is going to be that much warmer because of it. But it does mean that on average over the globe we will be essentially contributing to accelerating the warming that we've seen.
Okay, thanks. Here's one by Kim in Pennsylvania. She wants to know if and you may not know the answer to this, but is the Earth's orbit altering, and how would that affect climate?
So the Earth's orbit has cycles, kind of not built in, but it has cycles within it, and these have to do with the various wobbles in the way that the Earth has as it goes around the sun, and these different aspects of wobbling occur over thousands to tens of thousands of years, and they're known. The orbit itself, there is no evidence that the orbit itself is changing, other than it's naturally progressing through these various, they're called Milankovitch cycles.
Okay, and here's one from Ed, and he wants to know if you could comment on the HAARP, which is the High Frequency Active Auroral Research Program in Alaska, if that's having any effect on global weather. So this is where they with I guess the program puts energy rays into the sky from antennas in Alaska.
Yeah, I think they deal more with the kind of ionosphere and the electrical conditions related to that, and I don't think there's any connection with weather whatsoever. I cannot see a path where that would affect weather.
Okay, thanks. Here's one from Colleen, and she writes in, and Nolan may have some comments on this as well. Can you discuss how climate change will affect wildfire in the West?
Yeah, I would be happy to punt to Nolan on that as a local expert.
Oh, great. It is a depressing week here in Colorado with another round of wildfires, again hitting populated areas. It's certainly something that we ponder regularly, trying to figure out, is this onslaught of devastating fires predominantly climate-driven or predominantly socially driven, where we live, how fires are started and fought, etc., or is it ecological, the maturing of forests that are different now than they were 30 years ago, which are different by a lot than they were 100 years ago? And more than likely, it's a combination of all factors. It cannot be made as simple as saying, yep, it's climate change. It is just more complicated than that. But hotter, drier conditions more often will predispose that situation to occurring more often until the forest itself adapts by becoming a different ecosystem than it is right now.
Thanks, Nolan. Doug in northern Minnesota wants to know, have heat islands, urban heat islands around cities and airports affected continental temperature observations?
Yeah, so heat islands do influence the observations taken over time at a station, and there has been quite a bit of research into quantifying just how much they do and how do we do a good job of correcting for those. And there's a couple subtleties actually within that. It's really it's very straightforward to kind of point at a station that's located near an airport that's had a city kind of grow up around it and say, well, that station is has a warming influence from the city around it, and it does. And there are several different ways to kind of combat that. At NOAA, or at NCDC here, we essentially use the relationships between that station and its neighboring stations to determine what the influence is, if there are non-climate factors that are influencing that station. And so when we put that if there is a station that has a noticeable change relative to its neighbors in temperature, when we put it into the record, we will correct for that. And that change may come from an urban heat island effect. It may come from the fact that the station was moved from one point in the town to another. But basically, we have algorithms, computer programs, that detect these changes in the station history and correct for them. The other thing about urban heat island that not a lot of people have been exposed to is the urban heat island effect is often cited as we have these stations out in pristine locations in the airports, and the cities are approaching them, but what people often don't realize is when the station was moved out to that pristine airport location around World War II, it actually came from a very urban area. So for most of the cities in the U.S. that had that have an airport location right now, for the first part of the 20th century, they were essentially taking weather observations downtown as well. So the urban heat island effect is not just an issue in the later part of the record. It was a big issue in the early part of the record as well. And it's in terms of what influence does that have on the trend that you would see in that city, the urban heat island effect would actually warm the early part of the record a little bit artificially and the late part of the record a little bit artificially. So it's not just a one-way street like a lot of people assume that urbanization is the signal that we see in warming. I guess what I would say is we do detect it, we do correct for it, and it's not just a warming. It doesn't just add to the warming trend when the city grows toward the station in the later part of the record. Urban heat island actually can cause an artificial cooling effect if the station was placed within the city in the early part of the record, where it was artificially warmer at the beginning of the record as well. I hope that makes sense. But it's a lot more complex just than, urban heat island is causing a rise in temperatures. It's actually well known and corrected for.
Thanks, Deke. Here's another question from Laura in New Hampshire. She wants to know, what is it about the cooling stratosphere that creates a warm climate? Or is it the warm climate is the reason for the cooling stratosphere?
Yeah, so the cooling stratosphere, and the stratosphere is the next layer of the atmosphere above the troposphere, which is where we live. And the troposphere is anywhere from 7 to 10 miles thick, give or take. And then the next slab of the atmosphere above that is the stratosphere. And the reason that the cooling of the stratosphere is important in the context that the troposphere is warming, especially the lower troposphere is warming, is that if we see a cooling stratosphere, if the upper half of the atmosphere is cooling while the lower half of the atmosphere is warming, then the warming that we see here at the surface is essentially being done because the composition of the atmosphere has changed. And these are predicted. I mean, the cooling stratosphere wasn't the aha moment that said, oh yeah, it's greenhouse gases. The cooling stratosphere is absolutely what you would expect in a greenhouse gas warmed world. And what greenhouse gas related warming does is it tends to trap heat lower in the atmosphere so that the normal energy that would escape to space in a pristine atmosphere actually gets bounced around a little more lower in the atmosphere and warms the lower atmosphere at the expense of the upper atmosphere. It's just like when you put a blanket on in bed, The mechanism isn't the same, but you're effectively trapping your body heat closer to you to make that little shell that you sleep in warmer, and it is actually coming at the expense of the room. The rest of the room is a little cooler because you're doing that. And in the same way, trapping heat lower in the atmosphere, the same mechanism actually helps the stratosphere and the upper atmosphere to cool. And that's the relationship between that. And that is, again, it wasn't the discovery that that tipped people off to greenhouse gas warming. It's essentially, it was expected based on physics, and then the observations basically confirmed it, that it was happening.
I tell you, Deke, really appreciate those examples with the blanket, with Rocky, all those, common things we see every day. How to take those and relate the climate using those as examples is really helpful. Here is Tim. Tim writes in, and he's heard that the wind speed of the jet stream is increasing. If that's true, how would it affect our weather?
I have not heard that myself. We haven't seen that in the data. If anything, on average, because the jet stream, the reason it exists is it is kind of a manifestation of the differences in temperature and energy from the tropics and subtropics versus the kind of polar regions. So in many ways, the jet stream sets up where it does on any given day as something like the indicator of the boundary between where the warm area is and where the cold air is. It's a lot more complicated than that, but effectively in the long term, you can kind of say, okay, the jet stream is a feature that helps describe the boundary between the warm air masses and the cold air masses, and the speed of the winds within the jet stream are influenced by the temperature gradient beneath it. So if there's a very sharp, strong, dramatic transition from very warm to very cold, the speeds in the jet stream associated with that very sharp gradient are going to be a lot stronger. So one of the things, if you go back to one of the maps that we showed early on in the presentation, that the kind of poleward regions are warming more quickly than the equator regions, which means you're basically you're warming the cold regions a little faster than you're warming the warm regions, which over the long term kind of relaxes that gradient. It basically means that the transition isn't quite as dramatic, and that in the long term, again, in the long term, on average, not necessarily for any given day or any given place, you would expect the jet to actually weaken a little bit. And I honestly am not a jet stream guy, and I don't know what the data says. But I do know that one of the ingredients for tornadoes is wind shear, which is kind of related, and they have observed a slight decrease in wind shear, again, largely due to relaxing this gradient, this difference between the warm air and the cold air. Again, that's all, like everything I'm saying today, that's all averaged over the long term, averaged over many places, and may not and will not hold true at every given place at every given time.
We've got a couple minutes left for questions. We've got a few coming in here, and I've seen a couple here recently wanting to know about sea ice and ocean temperatures. Let me kind of try to combine all these. If the Arctic sea ice keeps melting, would that have an effect on our climate and weather changes? Would they be more severe? Another viewer writes in wanting to know if there's enough ocean analysis, enough data for ocean analysis. And then another question just came in on the ocean currents and global warming. So I don't know if we can kind of ball those all up into looking at the sea ice, looking at is there enough data out there, and then how do these currents affect global warming? If you just comment on those, Deke.
You bet. So the relationship between sea ice and kind of seasonal weather outcomes is really an active area of research, and the intuition is that if you leave more open water exposed as the sea ice retreats, how is the increased evaporation and heat that comes from those open waters going to influence weather patterns and climate variability patterns that play into our seasonal outcomes. And I'm behind on the literature, but I know it's really actively being researched, and I don't think there's a broad consensus on what that's going to mean. I think there's a lot of useful research, and we probably will know quite a bit more in a couple years than we know now. As far as ocean currents, again, changes in patterns of temperature and heating and density and salinity, the amount of salt in different parts of the ocean will have an effect on ocean currents. Again, I apologize for bailing out. I'm not an oceanographer. I don't know exactly how that would work from week to week or month to month. I do know one of the kind of long-term scenarios that gained some popularity a few years ago was about the disruption of essentially the Gulf Stream as part of this global thermohaline circulation, this kind of global ocean transport system. But that again is an active area of research that is well beyond my limited capacity as a meteorologist.
Okay, Deke, we've got one more question. We're going to end on this one today. Robert in Texas, and perhaps maybe you living in Oklahoma might be able to shed some light on this. With the storm spotters out there and the latest data and technology, he was wondering if there'd be a longer lead time on tornado safety. So do you think that'll lead to that eventually?
Yeah, so I'm just want to stipulate, I'm not speaking for NOAA here, because we have people within NOAA, and particularly in Norman, that really research and understand these things. So what I'm going to share with you is a product of me working back in Norman about 5 years ago, and I'm about 5 years behind the times, and I'm sure it's changed since I was there. But in general, yes, lead times have improved, and they are expected to continue to improve. And one of the real big questions from a social standpoint is, when does a lot of lead time become too much lead time? When does knowing 45 minutes in advance actually become a little more dangerous than knowing 20 minutes in advance, where people get a little complacent or impatient when they're taking their procedures? So I know that was, again, I'm speaking from about 2008, so don't take this as gospel, and please get a second opinion, because there's a lot more people that are a lot more plugged in than I am. But in general, lead times are improving, and they're expected to continue to improve. And then the next kind of bits of research that people are doing is, okay, how much is enough of lead time? When are you just telling people enough? And then there's a quantum leap coming sometime in forecasting, where they'll hopefully be able to begin to say a few hours in advance, we are confident there will be tornadoes in this particular part of the county because of the modeling that we've seen. And the technology and the science has a long way to go to catch up to that, but I know that there is a future that has that scenario in it, and I don't know whether it's in the coming decade or if it's in my children's time or grandchildren's time, but that's the next kind of quantum leap, and then we would be less worried about lead time and more worried about, okay, how do people respond when they're given a few hours or a day of lead time.
Yeah, and if you'd like to go back for our viewer out there, 2 months ago, Greg Carbon gave a great talk on tornadoes and all the advancements they're making there. That's on our WeatherTalk webinar website, and he's answered a lot of questions on there. In fact, it's interesting. Yesterday, one of the few times of the year we saw the high probability on the Storm Prediction Center for tornadoes in northern Illinois, Iowa, and Indiana, and they did have a few yesterday. So they're getting the word out a couple more days in advance as we see things move along.
And
well,
I would definitely go with what Greg says over what I say on that topic especially.
Deke, it's been a pleasure having you as part of our webinar today. Some really interesting stuff. You've cleared up a lot of things for us out there. And again, we'll record this. We'll put the links up for Hopefully have those up by tomorrow on our website. And again, this is recorded. We'll have that posted. And I hope we see you again soon. We'll probably run into you at a conference or two coming up.
And
Well,
Deke,
folks,
thanks so much for mentioning the value of the observations. People ask that time and time again. Do people really use our CoCoRaHS rainfall and snowfall and hail observations? And I think you've made that pretty clear, and thank you very much.
Absolutely critical, vital, potentially life-saving on the day of the observation, and a good map with lots of dots on it, with lots of rainfall, is going to make for a smarter America for my kids to grow up in. And we'll know more about climate and precipitation especially, and I'm really thankful for the service that all observers and CoCoRaHS observers do.
Thanks, Deke. Well, folks, we want you to join us for our next CoCoRaHS webinar, WeatherTalk webinar. That'll be late in the month in July, on the 25th of July. And if you've ever captured rainfall in your backyard to use, Billy Niffen of the American Rainwater Catchment Systems Association will tell us all about the ins and outs of rainwater harvesting. And it should be a very interesting talk indeed. We'll have stuff on our website on how to sign up for that. Well, folks, we've come to the end of our webinar for today. Please, before you leave, take the survey at the end of the webinar, and we want to wish you a good week and a good month ahead, and we'll join us again back in July. Take care. Have a great day.